Hi, uh, my name is Radilan, and I'm going to my team going to present project based learning engineering math 2. Okay. Our my team is Muhammad Shazwan Hakimi bin Shazul Nizam, Hui Peng, Alkina Sanajonik, and myself, Larry Allen, anak Peter. Okay, I will pass to Shazwan for the introduction.
Hi, my name is Shazwan. For our introduction is first order ordinary differential equation or DES are mathematical tools used to describe the rate at which a quantity changes in relation to another. They involve a function and its first derivative and are fundamental in modeling dynamic system where change occur over time or space. These equations are widely used in science, engineering, economic, biology, and many other fields due to their ability to present real-world phenomena in precise and predictive way. One of the key reasons first-order orders are important to their versatility. They can be used to model a population growth, radioactive decay, heat transfer and chemical reaction, and also the motion of object under the influence of force. In electrical engineering, they describe the behavior of circuit in economic. The model investment growth and resource depletion. The power of first order orders lies in their ability to relate a quantity to its rate of change. Solving this equation provide insight into how system evolve over time and making the essential for analyzing and predicting the behavior of natural and engineering system. So this is our filler table. So fact, the first order involve the first derivative of an unknown function. And then common use in physics, biology, economic, and engineering. So present in relationship between a quantity and its rate of change can be linear or nonlinear. So the idea is used to model real world problem, involve the rate of change, describe the process like population growth, radioactive decay, cooling or heat and motion, useful for predicting future behavior of dynamic system, and then often used in real time system simulation. And then this is our learning issue and action plan. So I will pass to question part A.
Question Part A. In large forest ecosystem, a population of wild deer is declining due to habitat destruction and deforestation and human encroachment. These environmental changes are reducing the availability of food sources, water, and shelter, leading to a steady decrease in the deer population. Conservation have recorded that in 2010 the deer population was 2,000. However, due to continuous habitat loss, the population declined to 1,200 by 2020. Studies indicate that the population decline follows an exponential decay pattern. Wildlife conservation agencies Agencies are interested in predicting the future population trends and determining whether intervention strategies such as protected reserve and reforestation can help prevent the extinction of deer in this region. A. Derive a formula for the deer population at time t. B. Predict the deer population in 2030. C. Determine when the deer population will drop below 500 deer. Bracket A. Critical threshold for conservation efforts. Question A. Solution. Step 1. Derive the formula. P bracket T equal to P. Question A. Solution. Step 1. Derive the formula. P P bracket T equal to P O E negative K T, where P T equal to population at time, PO equal to initial population at 2000. K is equal to decay constant. T is equal to number of years since 2010. Define T is equal to S 2010. So PO is equal to 2000. Now plug in the value for the 2020. T is equal to 10. P bracket 10 equal to 1200. 1200 equal to 2000 times E power of KT. Step 2. Solve it. Take natural logarithm ln of both sides. So and take the natural logarithm for both sides again. So K is equal to ln bracket 26 over 10. So K is 0. Negative 0.0508. So the final formula is PT equal to 2000 times with E power of negative 0.051.08 T. This equation model the deer population where T is the number of years since 2010. Solution for question B. Predict the deer population in 2030. Step 1. Set T is equal to 20. Since 2030 is 20 years after 2010, so P bracket 20 is equal to 2000 times with E the power of 0.05108 times 20. So simplify the exponent. 0.05108 times 20 is equal to 1.0216. The 20 equal to 2000 times E negative 1.0216. Calculate the exponential. E the power of 1.0216 is equal to 0.36. P 20 equal to 2000 0.36 is equal to 720. So the final answer is P 2030 is equal to 720 deer. For solution for question C, when we population drop below 500, we want to solve 2000 E negative 0.05108 T is less than 500. Step 1. Divide both sides by 2000. So E power of negative 0.05108 t less than 0.25. And step 2, take natural logarithm of both sides. ln bracket e negative 0.05108 t less than ln 0.25. Step 3, divide by negative 0.05108 and flip to the inequality. T is more than 1.3863 over 0.05108 equal to 27.4. So the final answer is the population will drop below 500 in about T is equal to 37.14 years after 2010, where it is on 2037. That's all for part A.
So, my name is Wei Peng. I will present question part B. The question is, one evening, while walking through your hostel, you come across a closed room and notice something unusual inside. Upon entering, you discover a dead body and immediately call the police. When the authorities arrive, they determine the core temperature of the body at the time of discovery to be 85 Fahrenheit. The room's temperature has been constant at 70 Fahrenheit throughout. After exactly 1 hour, the police take a second temperature reading and find that the body's core temperature has dropped further to 80 Fahrenheit. Assuming that the victim's normal body temperature before death was 98.6 Fahrenheit and the time of death corresponds to T is equal to 0, use Newton's law of cooling to calculate how many hours had passed between the time of death and when the body was discovered. Solution part B, question A, is about Newton's law of cooling equation. The equation is T bracket T is equal to T room plus bracket T0 minus T room e power of kt. So T bracket T is the temperature of the body at time. T0 is the initial temperature of body 98.6 Fahrenheit. So T room is the ambient temperature (70 Fahrenheit). So K is constant and T is the time in hours since that. So step 1, set up the equation for the time of discovery.
Let's say the body was discovered at time t after that. At the time, the body temperature was 85 Fahrenheit. So, sub in the formula, 85 is equal to 70 plus bracket 98.6 minus 70 e power of negative k t d. So 15 is equals to 28.6 e power of k t d. So we can solve it. 15 over 28.6 is equal to e power of negative k t d. So ln 15 power 28.6 is equal to negative k t d. This is equation 1. Step 2. Set up the equation for 1 hour after discovery. When the temperature was 80 Fahrenheit, so 80 plus 70 plus bracket 98.6 minus 70 e power negative k bracket td plus 1. So solve it. 10 is equal to 28.6 e power negative k td plus 1. So 10 over 28.6 is equal to e same thing. Okay, so ln 10 over 28.6 is equal to negative k td plus 1. This is equation 2. So step 3. Subtract equation 1 from equation 2. Let's subtract the equation. Ln 10 over 28.6 minus ln 15 28.6 is equal to negative k bracket td plus 1 plus k td. So ln 10 over 15 is equal to negative k. K is equal to ln 10 over 15 is equal to negative ln 2 per 3, and same with ln 3 per 2. So k is equal to ln 1.5 and 0.4055. Step 4. Plug back to find TD. Use equation 1. Ln 15 per 28.6 is equal to negative KTD. TD is equal to negative Ln per K. TD is equal to negative, bracket negative 0.644 per 0.4055 is equal to 0.044 per 0.4055, 1.588 hours. Approximately 1.559 hours, or about 1 hour and 35 minutes, has passed between the time of death and when the body was discovered. That's all. Thank you.
Discussion and conclusion. Okay. After studying the application of first order ordinary differential equation (ODES) to model the declining deer population, we obtain a clear understanding of how mathematical tools can describe real-world ecological issue. By assuming the population follows an exponential decay pattern, we derive a differential equation that accurately model the population decrease due to habitat loss and human encroachment. From this, we determine a decay constant using real data from 2010 and 2020, allowing us to create the population model PT 2000 times E power negative 0.05108 T. PT equals to 2000. Yes. Using this model, we predicted that by 2030, the deer population would drop to approximately 720 and more critically fall below the conservation threshold of 500 around the year 2037. This finding highlight the power of first order odds in forecasting population trends and emphasizing the urgency of conservation effort to prevent species extinction. For uh, part B, using Newton's law of cooling, we analyzed that the rate at which the victim's body temperature decreased in a room maintained at 70 Fahrenheit to estimate the time since death. Based on two temperature readings, which is 85 Fahrenheit at the time of discovery and 80 Fahrenheit 1 hour later. We calculate the cooling constant and determine the approximately 1.76 hours passed between the time of death and when the body was found. This method assumes a constant ambient temperature and no external disturbance, making it a reliable estimate under controlled conditions. While useful in forensic investigation, the accuracy may vary in real-world scenario due to factors like clothing, body mass, and environmental change. That's all from us. Thank you.